Hello nerds and welcome back to another exciting lesson of AP Precalculus. Get out of here. Today we're going to be talking about the 12 basic functions, at least that's what our author has dubbed them. I would argue there's probably some other basic functions, but I digress. The hope is that you already know most of these, but it's okay if you don't, because we'll just get good at them. That's the purpose of the lesson, right? What we're going to do is we're going to go through these 12 things and talk about some properties of them. And then we're just going to answer some classification questions about them. Really easy stuff. The first one, the identity function, y equals x. It's called the identity function because regardless of what x you throw at it, it hands you back the exact same number for y. Y equals x. Boom. What's wrong? It is the identity linear function, y equals x. Yep. Its domain is all the x's that it could cover up. Now the thing is, just an image of a graph, but clearly it's going to go on and on and on forever in both directions. And since it goes on and on for both directions forever, our domain will be all real numbers. And since the y's are exactly the same as the x's, it'll have an identical range. Arguably the most boring of the 12 basic functions. It's a her? Did you just assume this line's identity? Like gender identity? Okay. I'm not, I thought the joke, but I'm not saying it. You want to pipe? You want to get close to the mic? You could say it. Yeah, I heard you. No, get out of here. You're not. Keep your hate speech to yourself.
I was making an observation.
Oh, God, I know. We were all thinking it. It's okay.
I just said it.
The squaring function, this is y equals x squared. Okay. The reason why our authors don't say something like the quadratic is because technically every even power is a quadratic. So x to the fourth is quadratic, x to the sixth is quadratic, so on and so forth. Okay? So we call it the squaring function. Because you can square any number you'd like, the domain is all real numbers. However, something very special happens when you square a number. It guarantees not negative. So then the range of this function is from 0 to infinity, and it includes 0 because 0 squared is 0. Let's talk about some things that we learned from 1.2. It is decreasing on the left of its axis of symmetry, increasing on the right of its axis of symmetry. Because it has an axis of symmetry, we would say it has line symmetry. Because that axis of symmetry is the y-axis, we would say this is an even function. And it is bounded below because it has a minimum, which is its only extreme value. I think that was all the things we talked about. Oh, and concavity. It's concave up on its whole domain. There you go. Pretty cool, huh? What I just gave you is called a... I forgot the verbiage. I'm going to cheat and look at the verbiage. Ah, yes, complete analysis of the graph. A complete analysis is just basically saying all the things that you can see from 1.2. That's what a complete analysis is. The next two. This one, the cubing function, y equals x to the third power. Y equals x cubed. Because you can raise any number to the third power, its domain is all real numbers. And because raising 0 to the third is 0, positives to the third is positive, and negatives to the third is negative, and also because you can just see it, our range is also all real numbers. Some things from section 1.2. This is increasing on its entire domain since we use brackets for increasing, decreasing. So we can say that this thing is increasing on its entire domain. Why did I say it like that? Because right here at x equals 0, we have something called an inflection point. If you remember what inflection point means, it's a place where your concavity changes. Because to the left of this point, it's concave down. To the right of this point, it's concave up. At this point, calculus tells us that it has a slope of 0, which is not positive. But if we're going to use a bracket to say it is increasing until 0 with a bracket, and then increasing from 0 to infinity with a bracket, clearly we included 0, so we have to say now this is increasing on its entire domain. Okay? I've already covered increasing, I've already covered inflection, I've already covered concavity. I can't remember if I said it, but because this has a minimum, this is bounded below. I can't remember if I said those words. This is unbounded, but it does have symmetry. It is odd symmetry. It's an odd function because reflecting it over the x-axis, which means turning it upside down, would have been exactly the same as if I had reflected it over the y-axis, turning it left and right. So because reflecting up-down is the same as reflecting left-right, it is an odd function. Cool? Okay. The reciprocal function, it's called the reciprocal function because it's 1 over x. This one's domain is not all real numbers. Because there's one number in particular that you can never have on the bottom of that fraction. What is that number, class?
0.
0. So what we know is that there is an infinite discontinuity, a vertical asymptote happening at x equals 0. And what we can also see from this picture is y equals 0, the x-axis, is a horizontal asymptote. So talking about what we talked about in the last lesson, this is a bottom-heavy function. The degree of the x on the bottom is bigger than the degree of the x on the top. There isn't an x on the top. So this is bottom-heavy, which is why the x-axis, y equals 0, is its horizontal asymptote. So its domain is going to be every number except for 0, because you can't divide by 0. And its range is going to be every number except for 0. Because a positive number divided by anything you could think of will always be a number that's not 0. So the domain and range are identical. Some properties, the analysis. It is decreasing on its entire domain. Everywhere you draw, everywhere you let that roller coaster go, it falls. So decreasing on its entire domain. This side is concave down, this side is concave up. It has no extreme values. It is unbounded. It has odd symmetry. Reflecting it up-down is the same as reflecting it left-right. And another thing about it that's really cool, it is its own inverse. You don't have to know that yet, but it's a self-invertible function. It cancels itself, which is really cool. So if you reflect it over the line y equals x, it does this. You get the exact same graph. It's pretty neat. All right. Next. Speaking of inverses, kinda the inverse of the squaring function, the square root function. Now its domain is not going to be all real numbers, but it does not have a vertical asymptote. In fact, it has no asymptotes. It doesn't have any discontinuities either. It's just that there's a certain subset of numbers you cannot take the square root of. And those numbers would be negatives. But you can take the square root of 0. So your domain is from 0 to infinity. And as it turns out, the square root of every positive number itself is positive. And the square root of 0 is 0. So our range is also 0 to infinity inclusive on the 0. Complete analysis. This function is bounded below because it does have a bottom it can never go through. It does not have discontinuities. It does not have asymptotes of any kind, including horizontals. It is increasing on its entire domain, and it is up and to the right. on its entire domain, which means it is concave up on its entire domain. I know it doesn't look like the classic up and to the right arrow. I think I drew something like this in your notes. But if you read it as right and up, this is right and up. It's just facing a different direction, but it is still technically concave up because it goes right and up. Cool with that? Or am I talking out of my butt right now? I'm talking so out of my butt right now. Someone should take my degree and snatch it off the wall. This is concave down. It's half of this. It's concave down. So sorry. Anyway, it's concave down on its whole domain. No symmetries. None whatsoever. But it stops. It doesn't have to go down forever to be concave down. Concave down just describes its bend. That's if you go from left to right. But if you draw the 4 types of concavity things, these are your only 4 shapes. These are your ups. These are your downs. This is what the square root function looks like. Notice I didn't put any arrows on anything. It's just what the shapes are. Now, it goes up and to the right, yes, as x goes up, y goes up, but its bend is a downwards bend, even though it stops right there. Sorry about the confusion. Mm-hmm.
So it's increasing just concave down?
It's increasing on its whole domain, and it's concave down on its whole domain. Mm-hmm. And again, these aren't things you memorize. They're things you just look at and you see. So that's the good news. I'm not going to be like, quick, give me a function that's decreasing in concave down. You're like, oh, what? We're increasing in concave. You're like, you just look and say, oh, okay. Here we go. The exponential function, specifically base e's. This is e to the x. That is right, the number e. No, I'm not drunk. E is a number in mathematics. It's Euler's number, and that name starts with an E. It's French. E-U-L-E-R, Euler's number, and that's why we use an E for it. What? I know, right? French. How's this French toast? Smelling ungrateful, but this American toast is delicious. It's from a show. Anyway, Leonhard Euler is the mathematician that it's named after. I don't even know if he found it, but it's named after him. E. E is about 2.712-ish. It is irrational. It's like pi. It goes on forever with no pattern. It wasn't made up. It was discovered. Her face just crumpled up. What did I say that made your face crumple? No, something happened. I told you keep your hate speech to yourself. Okay, anyway. 2.718-ish. Kind of like how we say pi is around 3.14-ish. It's not 3.14. That's what we round it to. E is not 2.718. That's what we round it to. Or 71. Yeah, I said that right. 718. 71. Yeah, I can't remember. But the point is it's a rounded digits. Okay. Yeah, 2.718. Its domain, though, is what numbers could I plug in? Well, look. E is a positive number, and you can raise a positive number to any power you want, which means the domain is all real numbers. However, because E is a positive number, regardless of what values you raise it to, it can only give you back positive numbers. There's no way to raise a positive number to an exponent and get 0 as an answer. There's no way to get a negative answer. E is a positive value, which forces the range to be from 0 to infinity, not including the 0. That, ladies and gentlemen, is a horizontal asymptote. E is a positive number, yes. The domain are the x's you're allowed to plug in. But so it doesn't matter if you plug in a positive number or a negative number. E to a number is always going to give you back a positive result. So what about its analysis? Increasing on its entire domain. Concave up on its entire domain. That's not a mistake. It means that. Adi, you have a question for me? What's up?
Why is a number to the power of 0 still 1?
Why is a number to the power of 0 still 1? What a good question. Well, yeah, anything to the 0 is 1 except for 0 to the 0. But his question is why? I'm just trying to find a piece of paper I can write on. Here we go. Let's see. What is 2 to the first power?
2.
It's 2. What's 2 to the second power?
4.
2 to the third power?
16.
8. There. That's enough for, oh, you can't see it. That's enough for us to see this pattern. As you can see on the right side, as I go up an exponent, I'm multiplying by 2, right? Okay, so as you come down on this side, you're dividing by 2, right? 2 divided by 2 is 1, right? But on this side, going down requires me to subtract 1 from my exponent. And that's also why negative exponents move things across their fraction. Divide by 2, divide by 2, so on and so forth. Cool? Okay, so what we say, increasing on its whole domain, concave up on its whole domain, no symmetries, it's bounded below because of that horizontal asymptote. Is there anything else? No extrema. This one technically has a minimum, but no extrema here. Okay. Next, flip the page over. The natural logarithm function, the ln of x, this one is the inverse of the exponential e to the x. You don't need to know that yet. We'll handle those in chapter 3. For now, I just need you to be able to look at this graph and say things about it. First of all, its domain. It is a vertical asymptote. That is not a point of discontinuity. It's just where the domain begins. A point of discontinuity is specific to a value. This one has a point of discontinuity at x equals 0. This one does not have a point of discontinuity. It has an infinite number of discontinuities. No negative numbers. In fact, not even 0. So what we have to say is that its domain is all numbers greater than 0. However, it does go down and it does go up forever. So its range then is all real numbers. I would like for you to compare this one to the one we just did. Look at the domain and range. Look at the shape of the image. It's the same shape. It's just been turned sideways. The horizontal asymptote here is this one's vertical asymptote. Why? Because the domain and the range have switched places. Why? Because they're inverses of one another. Don't worry. Chapter 3. The analysis. Increasing on its entire domain. Concave down on its entire domain. No symmetry, no extrema, and it's not a bounded function because its range is unlimited. Cool? The sine function. We will get very, very familiar with trigonometric functions after chapter 3. Chapter 4 starts trig. This is the sine function. It is a coincidence that the abbreviation of the word sine is a word in English. That is a coincidence. You will not say sin of x. I will correct you every single time. It is a sin to use the abbreviated name of sine. Yes. A sin of the only commandments that I really care about, and they're the McCutcheon commandments. Thou shalt not say sin of when you mean sine. There's other commandments over there. It's like, or somewhere. I used to have a poster, thou shalt not write in pencil or in pen. Some bull stuff like that. But you will never say sin of x. I will correct you every time. So why does it say that on the calculator? Okay, someone please tell me, what is this an abbreviation for? Appointment. When's the last time you heard somebody say they had a doctor's appointment? Never. Because we don't say the abbreviation, we say the word.
Well, if I said WTF in school right now, you would be pretty upset. But since I'm saying
Just because I understand what it means doesn't mean we should talk that way. Text messaging has completely degraded the English language. In fact, there has been research done on this that shows that since the advent of text messaging, the average English vocabulary, like people's vocabulary, is getting smaller because we've bastardized our own language to save for characters. Anyway, my point is, it's a total coincidence that this abbreviation is a word in our language. Okay? So, sine of x. Its domain is all real numbers. As you can see, it goes forever from the left to the right. However, it is a bounded function because its range is locked between two numbers. -1 to +1 inclusive. So this is a bounded function. Other things. It has infinite zones of increasing, infinite zones of decreasing, infinite zones of concave up, infinite zones of concave down. It has an infinite number of local mins, an infinite number of local maxes. Will they have the same value? Yes. The local min of the parent function will always be 1. The local max of the parent -1, excuse me, and the local max will always be +1 because it's going to bounce between those two values. Now, as far as symmetry is concerned, the sine function has odd symmetry. Turning it upside down is the same as turning it left and right. So this function has odd symmetry. This is the cosine function. Not cos, not cos. Not appointment, sine, cosine. We don't use abbreviations when we say words. The cosine function. You will notice it's remarkably similar to the sine function. In fact, everything I said about the sine function is true about the cosine function except for one major thing. It is not an odd function. The cosine function is even because it's symmetric around the y-axis. So its domain is all real numbers. Its range is -1 to +1. It is bounded. And all the other crap I said about infinite mins, maxes, zones of increase, decrease, concave up, concave down, all that's still the same. This one just happens to be an even function. This is the absolute value function. Hopefully you're very familiar with the absolute value function from Algebra 1. People think absolute value turns things positive. That's not actually what absolute value means. Absolute value actually means how far is that thing from 0. That's what it means. And since there's no such thing as a negative distance, it turns negative numbers positive, but it actually means how far from 0. And that's a very important concept because later on in the year, we're going to use things that look like absolute value bars, but what they literally mean is how far from 0 is that object. You'll see what I mean in chapter 6, so quite a while from now. But anyway, its domain. Well, you could always say how far away any number is from 0, so its domain is all real numbers. But since there's no such thing as a negative distance, the smallest distance we could possibly have is 0, we have a function that is bounded below. Its range is from 0 to infinity. It is an even function, symmetric around the y-axis. It does not have concavity because it's not curvy. But it is decreasing to the left and increasing to the right, just like the squaring function is. And I've already said it's bounded below. I think that's everything. Buddy old pal, greatest integer function. It goes by many names. The greatest integer function, the floor function, a step function. Now, you notice how I said the, and then I said a step function? That's because there are other step functions. This is the greatest integer function, but there is also a least integer function. This is the floor function. There's also a ceiling function. It's shaped just like this, except for its horizontal segments are in a slightly different place. You might be looking at this going, why, mathematicians, why? It actually has real-world use. Electricity. Electricity is either on or off. There is no in between. And that's why there are no y values in between. You either have current or you don't. Okay. Also, the step function can be used to model current in objects. But the one that I always like to talk about, because it's really kind of funny, because dang nature, you're scary, is the physics of how electricity works in the ground. If you ever see a power line, a live power line, you'll know it's live because they're bright and loud. But if you ever see a live power line on the ground suddenly close to you, do you know how to escape with your life? And if you try to walk away, you turn into a puff of dust. Hop away is the correct answer. You hop away. The reason why you, that's why, oh, your dad's an electrician, that's why you know. Because electricity, it flows through ground like ripples do. So imagine ripples on the ocean on the surface of water, where there's peaks and there's valleys. Imagine though that those are now steps. The ripples are literal steps in the electricity, where one side of the ripple has one type of current, and the other side of the ripple has another type of current. And if you step across it, 1 foot in one zone and 1 foot in the other, the currents will equalize as they pass through your heart. And you will go poof, and you die. But if you hop away, worst case scenario is your feet land on a boundary zone. What happens? It hurts. The electricity equalizes through your foot. It went from like heel to toe. It didn't have to pass through your heart. So it hurts. But you live. It's literally called step voltage. That's what it's called. So, what's that? No, because if ever you have both feet on the ground for an instant of time and you are in two different voltages, you dead, son. So no. No, you can hop on 2 feet because worst case scenario, your foot lands on the boundary zone and the electricity equalizes through your foot and not through your body. So it'll hurt. Yeah, but if you hop on 1 foot, you might fall. She's gonna hop scotch. Skipping to safety, skipping to safety. She's gonna hop. And you go home and you tell Pops about it, okay? Anyway. Psst. We gotta get back to it though. So there is one other way that you could see this thing written. It could also be written like this. And that's, wow, that looks like I tried to connect the dots, doesn't it? Yeah. There. Because it's the floor function. So we could say int of x, it could be this double bracket x, or it could be, I don't even know what you would call those symbols, but I'd say that's floor of x. L's in reverse L. What does the floor function do? It rounds down to the last integer value that was less than or equal to the number you just said. Basically, if you input a decimal answer, it rounds down to the integer before. So you say, what is int of 1.3? It says 1. It says, well, what is int of 1.7? It says 1. What is int of 1.99999? 1. What is int of 2? 2. Because at every integer value, every integer is less than or equal to itself. This thing rounds down to the greatest integer that was less than or equal to what you just said. So it's actually really easy to understand how it works on the positive side. The negative side is what starts to get people. Could you say, what is int of negative 1.1? The answer is negative 2. Because you're rounding down. And negative 2 is less than negative 1. So you're rounding down to the greatest integer that was less than or equal to what you just said. Okay. Its domain, though, is all real numbers. You can plug in anything you want. It's ready to rock and roll. But I would like for you to look at the y values that it covers up. There are no decimal y values on this graph. So the only way that we could say what its range is by writing a word. The range is all integers. It's neither increasing nor decreasing. I think technically it doesn't have symmetry. It's got no concavity. It's a thing. But you know what it does have? An infinite number of jump discontinuities. And do you see where the jump discontinuities are occurring? At the integer values for x. At x equals 1, there's a jump. At x equals 2, there's a jump. At x equals 3, there's a jump. There's a jump discontinuity at every x value. That's an integer. However, every one of those x values is on its domain. If you took this thing and smashed it flat, every one of those dots would fill one of these dots. And you would have a solid line. The open and closed.
Those dots, what are the dots here? We're not talking about that one.
Yeah, I'm not on that one.
Oh, okay.
She's looking at the wrong picture. All credibility just went out the window with you. Okay, next and last, the logistic function.
Now we're talking about this one.
Now we're talking about this one, and you might be thinking once again, why, mathematicians? Why? I'll tell you why. It's because it is very useful for modeling populations of things. Population growths and carrying capacities. Virus growth. During the COVID pandemic, you heard a lot of news outlets talking about we need to flatten the curve. I'm sure they didn't know what they were saying. But what they literally meant was we needed to get out of the steep zone of this curve and start to get into the flat zone, where the number of infected was not increasing per day, but was maintaining. That's what flatten that curve means. This thing has a domain of all real numbers, but the range is locked between 0 and 1. This is a bounded function. It has two horizontal asymptotes, one at the top and one at the bottom. The horizontal asymptote at the top comes from that digit. Why are people packing up? I was just saying, we're here until 11:08. I got time. Okay. This function, increasing on its entire domain, concave up, concave down. No extrema, no symmetry. If this point was sitting right there, I can't say, okay, it has point symmetry, but it does not have odd function symmetry. It is point symmetric around this inflection point. But because this inflection point is not at the origin, we don't have odd symmetry. I think that's all the things. Yep.
Range, like the one for range, what that,
How what?
why is there, I don't,
Well,
they're blacked out.
imagine the bottom of this fraction is always going to be a number that's not 0, right? But since it says 1 plus or 1 minus, it can't ever be 0. What it could be is huge positive numbers, which would have this go to 0, or remarkably small numbers, and 1 over remarkably small, well, let's say this different. This e to the negative x, it can become remarkably small. So the smaller this thing becomes, the closer the bottom becomes to 1. And 1 over 1 is 1. But they'll never actually be equal to each other.
Oh, no, okay, never mind.
Good?
I understand what you were explaining. I just didn't see it as like bounded by one.
Oh yeah, it's bounded up there. And down here.
I didn't see that. That's where the one was. I was using that.
Okie dokie smoky. All right, flip it over. Now we're going to do a bunch of questions where all we do is classify stuff.
Yay.
If you look at the 12 functions, there are 3 of them with restricted domains. Who can give me one with a restricted domain? Just one. I need one. Adi, give me one.
Natural log.
Natural log. Yes, has a restricted domain. Who can give me another one with a restricted domain? Somebody else. I was say somebody shouted it, but the reciprocal function. And one more with a restricted domain. Somebody new. Okay. For some reason, I'm struggling right now, but I know your name, and I've said it lots of times, but I forgot it. What is it?
Charlie.
Charlie, I knew that. I'm sorry.
Square root function.
The square root function. Thank you. One of the function's domain has a set of all real numbers, except for the number x. And the number x, the number 0. Which one is everything except for 0? The reciprocal function. Right. But why? Yeah, because the denominator can't be 0. You can't divide by 0. Duh. That's why. Two functions have no negative numbers in their domains. Who can give me one? Absolute value is 1. You guys, I'm trying to learn names. So absolute value. What's the other one with no negative numbers in their domains? I'm sorry to start calling on random victim. Okay. Hold on. Travis.
Yeah. Natural log.
Natural log has no negative numbers in the domain. Good.
Why can't this absolute value and absolute value be 0?
Yeah. Because what absolute value means is how far from 0 is this?
0 is at 0.
So you go, it's 0 away from 0. Yes, Adi?
Is that square root? Yeah, the absolute value.
Oh, I wrote absolute, that's domains. I mean, ranges. Ashley, you messed up my video. Gosh dog it.
What I do?
It's not absolute values. That has no negatives in its range. You were so convincing I believed you. Yeah, it's the squaring function. Anyway, which one of those is allowed to have x equals 0? Square root. I'm so flustered right now, these square root. Yeah, you did, because I'm trying to finish this video in time.
You would be a really good politician. He didn't even question you.
I think I've just been trained throughout the years to just see like, oh, a woman spoke, yes, you were right, because it's easier than arguing. Okay, anyway, looking at continuity. Only 2 of the 12 functions have points of discontinuity. Which ones? Adi, give me one. Reciprocal has a point of discontinuity, and what's the other one that has points of discontinuity? Yes, Kate says greatest integer. She's right. Here's the question. For the reciprocal function, is x equals 0 in the domain? No, it is not. The greatest integer function has points of discontinuity at every integer value of x. But does that graph exist at the integer values of x? Yes, it does. Three of the functions are 100% bounded above and below. Someone give me one. Mark. Logistic. Yes. Give me another. Cosine. Thank you, sir. And lastly, and I'm just trying to get new people. Like, yes. Cole.
I don't know.
Just look. Listen. Listen.
The sine function.
The sine function. There it is. Awesome.
I said it though.
3 of our functions have even symmetry. Now, Ashley. Oh, that's not what I was going to say, but okay, she says cosine. I called on you specifically because, Adi, the absolute value function, which is why I called on you, Ashley, because your absolute value function is an even function. What's the last one that's even? No, the identity is actually odd. Even means that it's the y-axis cuts it in half. Well, squaring, but yes, quadratics are, but we say squaring. All right. Regardless of if the video finishes, homework is still due, so we need to hurry. We need to listen. We're going to graph this thing. Its vertex is at 2, 0. X equals 2 is its axis of symmetry. Don't worry, we will review quadratics in chapter 2. If you plug in x equals 3, you get 1 and reflect it over. And if you plug in x equals 4, you get 4 and reflect it over. Don't worry, we will review quadratics in chapter 2. The purpose of this lesson is to be able to identify things of graphs. Which side is it increasing on? The right side. So we would say from 2 to infinity. That means it decreases on the left. From negative infinity to 2. As a class, I want you all to answer this next one. Even, odd, or neither?
Even.
Everybody said even. Everybody's wrong.
Neither.
It is neither even nor odd. It was a trick. I'm not mean. This graph has line symmetry. However, that line of symmetry is not the y-axis, so it is not even. It's actually neither, because it's been shifted. Does it have extrema? Of course it does. It is a minimum at x equals 2. Extrema means minimums and maximums. And how is it related to y equals x squared, Adi?
It's shifted to the right too.
Yeah, it's just shifted right to. It's just simple stuff. The next question. Does this graph have a horizontal asymptote?
Yes.
Horizontal? No, it doesn't. No. Because its range, remember, its range is negative infinity to positive infinity. It goes up forever. It's just really slow. And the last one, we actually already did it. When you go to do your homework, when it says analyze, that just means say all the things you could say about it. Well, we're just gonna say describe it. Congratulations, nerds. We made it. But barely. Good Lord.